Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Although it's been a few weeks since I've been recording here, I am uploading a video since our holiday break, and we are into a new semester here. Although this content will be kind of familiar to something that I did at the tail end of the semester, we are going to be looking at simplifying expressions that involve rational exponents and radicals. Some will get a little more complex. These come in 3 levels. I didn't make these problems, so I don't dictate, what makes a level, so to speak. But I can say with full certainty that some of the level 3 problems will be a little harder than, levels 1 and 2 when we work on them. Now, my video content will be slowing up a little, like the rate at which I upload videos. I'm not going to be making solution guide videos for every single topic. At least that's not the plan. As well as a math teacher, I am also a softball coach, and I coach both high school ball and travel ball. And now that high school ball is getting into almost full swing as we're conditioning now, it really does take up a lot of my time. I do private tutoring outside of this as well, and just it takes it up. And obviously my job comes first, but this was always supplementary to begin with. That's not to say we can't do things with my own students in the classroom and such, but it's not just for my students to know. For anyone who's watching these, just understand that some of these will slow up the rate. The other couple reasons for this are this. My videos are always meant to be trying to future-proof things for, later years. So I don't have to record all the time every single year. Maybe one day I'll be set. I'll be done. I don't have to record anything. I can just link those for my students. It's not always new content. Not always necessarily the case. Maybe I teach a different course. Like, I want to do pre-calculus next year. Maybe do a different course, and I got to do more material like that. We'll see how much I do there. Maybe we do a different book, so I got to make sure to cover some things based on either what that book shows or what kind of content's in there. So a lot of different things can happen when it comes to me recording more videos, even if I feel like I'm set and done for the current classes that I have. But the other thing is that we went into, per COVID, we went into distance learning. We went from distance learning into a hybrid learning format, and then I started to make some lessons, less solution guide videos and more lessons at the tail end of the year for 2 of my courses. And within those courses, those lessons were used for students who were potentially absent, who couldn't miss anything, and we did a flipped classroom model. So what that meant was I could use those for future years, and that's probably what I'm going to be using once we hit around April or something like that. So a lot less videos even at that time as well when it comes to it. But anyway, so with this one right here, what we're going to be doing is we're going to be reviewing and doing, I think it's 20-ish problems, 20-something problems on simplifying radicals and rational exponents. I'm not going to throw out all the properties there. Some of it's going to be assuming that you know some of them. Maybe I'll build some of the properties as I go, but I'll be saying them out loud, of course. And the problem with these kinds of videos all the time, of course, is that there's more than one way to do a problem. And I don't know how long I'm going to spend doing multiple ways for a single problem. I may or may not. Depends on the nature of the problem, of course. But it's not my way or the highway, but hopefully as I start to do something a certain kind of way, I can just be consistent with it. And maybe that's something that you flow and jive with, All right, so I'm just going to go ahead and get started, guys. That was a lot of talking. Let's go ahead and get going. And this is, like I said, there are 3 levels to problems here. And by the way, with the little amount of room, I think what I'm going to do is I'm going to do the work for a problem, and then I'm going to go ahead and write the answer here. And then I will erase the work here. And then I'll do work for the next problem right here, write its answer, and keep going into the next problem, etc., etc. I hope that's okay. And then you can rewind or fast forward and find the certain moment. Otherwise, it gets really cluttered. All right, so there are level 1 problems right here, numbers 1 through 7. It's these problems involve basic ideas. Most should be able to be completed in a step or 2, depending on the properties that you use and how much you need to write out. Level 2 problems, these problems involve multiple steps. You can kind of see that there's just a little more complexity to them once we get to those. And then level 3 on this next page here. Whoa. If you could do these, there's nothing on the quiz or test involving that you cannot handle. We can make things that are a lot more difficult. But actually, some of these problems are relatively easy in comparison, really. They are. They could be level 2, in some cases level 1. So let's go ahead and get started on these guys. Level 1 problems right here. We will start with problem number 1, where we have 81 to the 3/4 power. Now, as far as simplifying these things go, we must evaluate what this thing is. You could type it in a calculator and you'll get an answer. But what we want to do is figure out how we can kind of do this on our own. The idea behind this, and I'll go ahead and write this property because this is the crux of radicals and rational exponents. If we have a base raised to a rational exponential power, a rational exponent with a fraction, the denominator of this thing represents the root in a radical, and then you would have then the power as the numerator of that portion right there. Now, this is one way that it can be written. The other way that it can be written, and that it's most often processed by us, all depending on what we're doing, is we can take the root first, and then we raise it to the power. These are all equivalent. Saying it like this kind of looks like you're raising it to the power first and then taking the root, versus taking the root and then raising it to the power. Either or, you should be achieving the same value with the kinds of problems that we're doing. And that's kind of what we're going to do here. We understand 81 to the 3/4 power a lot less than we would understand the 4th root of 81 to the 3rd power, like this. We can take the 4th root of 81 to begin with, and that's what I'll do. I'd rather take the 4th root of 81 than cube 81, get a large number that I don't even know what it is, and then take its 4th root, which I wouldn't even know how to do. But I do know the 4th root of 81, and that value is 3. And we take that 3, and we are going to cube that value, and we get 27. So 27 is the answer to this one right here. Let's go ahead and box her up and set her off. And that is number 1. That's how we're going to evaluate that. Number 2. This is 27 to the, I'm going to say this is the negative 1/3 power. That's what I've been going with my kiddos, and I'm just going to go ahead and assume that that's what we're doing there. So 27 to the negative 1/3 power, like that. So a negative exponent can be turned positive if you change its place in its fraction. And there's no fraction here in 27. It's 27 over 1, though. So if we place the 27 in its denominator, leave, a 1 on top, then we'll be able to convert it to its positive exponent equivalent. So 27 to the negative 1/3 can be rewritten as 1 over 27 to the positive 1/3 power, like so. Okay, let me go ahead and write that property. I stated I wouldn't write them. I think I just meant that I wouldn't write them in the beginning, but here's one of them. And, there's an equivalent that states that you can go ahead and take a negative exponent in the denominator and make it positive in the numerator, just like that. So either or. Right there. Now, we're not done with this the same way as we weren't done with 81 to the 3/4 power. We must evaluate 27 to the 1/3, keep the 1 on top as we keep working. So 27 to the 1/3 power, in the same vein as the previous one here, the 3 would represent the root, so we're taking the cube root of 27 to the 1st power, which will just stay 27. So we have to take the cube root of 27, and that is 3. So we will get 1/3 from that, and 1/3 is then the answer. That is the simplified version of that problem there for number 2. Okay, so here we go. That is number 2. Let's erase that, as I promised. And let's go to number 3. Number 3 actually isn't a problem involving radicals, or rational exponents. So, take it as you will, but I'll go ahead and do it. So this property, there are 2 different properties I'm going to be using here. First of all, understanding this is a product, 3 times x squared times y cubed is all being cubed. What we're going to do is in a product raised to a power, you get to raise each factor to that power in said product. This is also true for division with a quotient, with a fraction. So if you raise this to a power as well, you can raise them to powers. So the first property I'm going to be exercising is the one, I should probably box these, with the product right here. And, 3 is a part of that product. A lot of people actually tend to skip the 3 of it, in and of itself. They kind of treat 3 as being part of the x squared. And then they completely ignore the 3 when it comes to cubing it. But no, we are going to be cubing 3 as well as x squared and y cubed. So x squared gets cubed, y cubed gets cubed. Now 3 cubed is 27. I can write down here because I'm going to erase this later. 3 cubed is 27. Next property that we're going to be using in terms of having x squared cubed is that when you raise not a power to a power, but this whole thing to a power, these 2 exponents end up multiplying with each other, x to the m times n power, like so. This kind of falls in line with what we did with this radical one, right? If these divide, then it represents a root, but if they multiply, then it represents an exponent. So it kind of falls in line with that. I mean, it very much does, but this is where you can relate them. So what we're going to do is multiply the 2 with the 3. So this becomes x to the 6th power there. So we're not doing 2 cubed. If this was a 2, we'd be doing 2 cubed to get 8, but this is 2 times 3. This is 3 times 3 right here. This is y to the 9th power, like that. So this is this answer here. Again, no rational exponents, no radicals were involved in the making of that answer. and 27x to the 6th, y to the 9th. I think there's another problem that's like that. Looks like number 6 is like that as well. And then I think all the rest do involve rationals, radicals or rational exponents. Okay, number 4, 8 27ths to the negative 2/3 power. And hopefully you can see the negative there. Now, I will be dealing with making it positive first. And I think in that vein, I should also mention that if you do have, we have something both in the numerator that technically could be raised to a negative exponent because of use of this property here. And the denominator would also be raised to a negative exponent. So numerator value would turn positive in the denominator. Negative denominator exponent would turn positive in the numerator. Therefore, these kind of flip if you want to turn this thing positive. And so the property that you can just write alongside that is that if I do have a fraction raised to a negative exponential power, if you want to make that thing positive, you flip your exponent like so. And that is exactly what I'm going to be doing right here to get it started. I'd rather deal with positive exponents pretty much as soon as possible for the majority of problems that we have. So this will turn into 27/8 to the positive 2/3 power, like that. There's more work to do with this one, obviously, as I'll have because of the... some of the simplification rules is we shouldn't have parentheses in our answer. We shouldn't have negative exponents, and we shouldn't have fractional exponents either. We should have integer exponents, and we should be evaluating our numbers as well. And anything that's left as a fraction, meaning we couldn't fully pull something out, like with variables, we'll write in radical form. So I'm sure we're going to run into at least one of those. So anyway, I'm going to be using this property right here where you raise both parts of the fraction to the power. The numerator, 27, is raised to the 2/3 power. And then the denominator, 8, is also being raised to said 2/3 power. I'll continue down here. To the 2/3 power means cube root of this number squared. And of course, like I stated before, I'd much rather take its cube root first before squaring it. I don't know 27 squared. You can figure it out, but I'm not going to. And then the cube root, whoopsie. And then the, and then the cube root of 8 is also getting squared like that. The cube root of 27 is 3. And then 3 squared will give us 9. And then the cube root of 8 is 2. And then 2 squared is 4. If you're curious how I'm nabbing cube roots, fourth roots, things like that, you are asking yourself what number times itself 3 times would give you 8 and would give you 27. That's what it means, as in 2 cubed is 8, 3 cubed is 27. At some point, you kind of just know them, right? So as far as how I'm getting them, well, I know them. Not all of them, but I know ones that show up quite often. If you know your perfect squares and perfect cubes up through, if you know your perfect squares up through like 16 or something, you're in pretty good shape for a lot of problems. There are some numbers you could skip sometimes. Perfect cubes, probably want to know them up to 10. I think that would be wise up to 10 for you to know. There's some, like sometimes 8 cubed. I'm like, is it this number or that? All right, number 5, cube root of 27, x to the 9th, y to the 12th. Now, very much like this product thing, remember, exponents and radicals are all really part of the same family, or powers and radicals. They're powers and roots. They're all part of the same family. Just like how multiplication and division are involved in the same family, addition and subtraction, rules that apply to one do apply to the other. So same thing here. When you look in an exponent, a radical really is a fractional exponent. So when you see this property, when you have a product raised to an exponent here and it splits these things up, you can do the same thing with radicals, in that if you take the root of a product here, then you can split this up into a product of 2 roots. The nth root of x times the nth root of y. And of course, if it works with products, it also works with fractions. So the nth root of x over y would also equal the nth root of x over the nth root of y. So I bring that up because number 5 shows exactly that, where we have a cube root of 27 times x to the 9th times y to the 12th. So that'll give us the cube root of 27 times the cube root of x to the 9th times the cube root of y to the 12th power. Now, cube root of 27, we've seen it a couple times. That number is 3. I'm going to go ahead and do that straight up. The cube root of x to the 9th, I dove into going from this way to this way. Well, now let's reverse that, right? What we're going to do, and I don't have to write it like this. I'll write it to begin with so you can see it. The nth root of x to the m power is x to the m over n power. So the cube root of x to the 9th power is x to the 9/3 power. I'm going to divide 9 by 3. I'm going to divide the power by the root. And that'll leave me with what the ultimate exponent is when I've simplified this thing. This becomes x cubed. 12 is also going to divide by 3 for this exponent for y, and that will become y to the 4th power here. So it's something to be careful of only because, I didn't divide 27 by 3, right? Exponents have a different story to them. They represent something different than actual values. Exponents describe how many times the number is multiplying to itself. Roots describe how many of something you have to multiply to make your thing, right? So they interact differently than a base value does. This wasn't 27 over 3, but this was 9 over 3. This was 12 over 3. So, there's just a different thing occurring in one versus the other. And it's best to trust the things you always knew how to do. Like, I'm sure you knew cube root of 27 probably before you knew this property. And then learning why this property exists the way it does is something that you can fall into while still maintaining what you always knew. See, the one problem that students will tend to have is they'll take something they always knew how to do and they'll change their mind on it because they learned a new property. Always trust what you always knew math-wise before you do that. All right, number 6. Again, this is non-radical, non-rational exponent kind of deal. It does have a negative exponent, though, and I've always told my students that I want to deal with negative exponents as soon as possible if it involves a fraction. I think it's just easiest to deal with, so you're not subtracting negatives and having something like that. So a negative exponent in the denominator means a positive exponent in the numerator. Y to the negative second power down there will become y to the positive second power up here. And that's where it goes. So now it's gone down here essentially, and it's going to multiply with the y cubed. So in just one idea of a step here, 3 isn't interacting with anything. 3 will remain a 3, and y cubed times y squared is y to the 5th power. Now I didn't forget x. X over here has x squared over x to the 5th power. One convention property-wise, alongside actually when you multiply here, if I multiply two identical bases with some exponents, you get to keep the base and add the exponents. Likewise, if you divide two identical bases with exponents, you would keep the base and subtract the exponents. So, one version of this that we could absolutely do is we could take this and turn this into x to the 2 minus 5 power, right? X to the 2 minus 5 power is x to the negative third. But, our final answer shouldn't have negative exponents, so I'd have to turn it into 1 over x cubed, bring it to the denominator. I have I'm not going to say a cleaner way of doing it, but it does, I think it's more efficient. I have a more efficient way of doing this, which is taking, there are 2 x's multiplied on top. I'm going to cancel them. I'm going to divide them with 2 x's multiplied on bottom. There are 5 x's on bottom total. But if I remove all 2 on top, and then 2 of them on the bottom, you're left with 3 on the bottom. You are literally left with x cubed on the bottom. That's what we were kind of talking about. This in the numerator is x cubed in the denominator. So this becomes all over x cubed like that. I sure hope to run into more problems where I can do that kind of thing and reinforce it for you along the way. Oh, and I totally disregarded the fact that I didn't mention this property when I added these 2 exponents here. I apologize. But y cubed times y squared, you don't multiply these exponents, you add them because of what exponents mean. That you're multiplying 5 y's total altogether. So this becomes 3y to the 5th all over x cubed. What time are we running on so far? Already 18 minutes. Geez, we're still in level 1. Maybe all the other problems I can explain less on the on the formulas, on the properties, and I can explain more on the strategy of the problem that I'm actually going to be doing itself. Okay, last problem on level 1. This is number 7. Here we have x cubed times x all over the square root of x to the 8th. Now, a couple implications that we have to throw in here. I mean, they have the implications, but a couple things we need to spell out, we need to infer, is that x means x to the 1st power, and that can help you with the idea of the property that you do add the exponents on top. X cubed times x to the 1st power is x to the 3 plus 1 power, or x to the 4th. On bottom, a square root has an implied value for its root as well, and it's not 1. If you take the first root of something, I don't know if we really call it that, but if you take the first root of something, you're not taking its root. It just remains what it is. A square root is the inverse of squaring something. Squaring something's raising to the 2nd power. Square root means the 2nd root. So we're taking the 2nd root of x to the 8th power. And that helps us because I'm not actually taking the square root of a number. I'm not evaluating a number. This is a variable raised to an exponent. So how do we clean it up? Well, like we saw before, we get to divide this power with this root. That's 8 divided by 2, which becomes 4. This is x to the 4th over x to the 4th, which when you divide something by itself there, you do get 1. Now, one other thing I'll throw in, I don't think it has to do with any of the things we're doing here, but x to the 0 power is 1. And here's kind of a way that we can show that. If something divided by itself is 1, and if you divide two identical bases, dividing two identical bases means you subtract your exponents, that becomes x to the 4 minus 4 power, which is x to the 0 power. Well, it seems to be no coincidence that you do get 1 out of it. And it kind of shows why 0 to the 0 power wouldn't give you 1. It would give you, you do 0 over 0. You can't divide by 0. So there's something to that as well. Anyway, this answer is 1. I don't think any x to the 0 powers show up in here. That's why I said I don't think it really matters, but there's the property. And that might not run the gamut of the properties, but that's quite a good handful there. And I don't know, I can drag them down with me, I suppose, but I think I need more work here. So really feel out the properties that we did just play with. Make some sense of those as we move on. Okay, level 2. Hey, these problems involve multiple steps, not unlike the other ones, but see if you can break the complicated problem up into its smaller components. Now, some problems are arguably still fine. It's just another step involved and you're good, but sometimes you're just asking where's a starting point. Number 8 can have several starting points, and I really struggle sometimes where I want to decide to go with it because I can involve multiple ways. I'll show you 2 ways for number 8, but that's not going to happen for every single problem. Once we realize a method that really works for us, I think we got to kind of stick with it. So number 8, there are kind of 2 different things you can do. And, when they say break it up into smaller components, it's because there is a square root, and then there's also the rational exponent. I mean, which do you tackle first? Do you tackle both at the same time? You could tackle both at the same time in that you could integrate them together as one thing, but I wouldn't actually literally say, let's do this part and let's do this part in with here. One thing I'll say for sure that I will not do first, this is our first time that we're seeing a numeric value raised to a numeric exponent, an integer exponent waiting for us to evaluate. Well, I'm not going to sit here and do 16 to the 8th power. I think something within this problem says that if we treat 16 more like a variable, and what I mean by we don't touch the 16, it just kind of sits there like an x, and we interact with the exponent a little more, maybe we can make the exponent smaller. And so then we can do 16 just to the 3rd power, which is actually still pretty big. Hopefully it's just 16 or 16 squared as we move forward. Anyway, maybe we don't do the square root and the exponent at the same time. Maybe we just do one and then deal with the other after. What if we ignore the square root? And by ignore, I mean, just draw it. And then we deal with the 1/2 here. And in dealing with the 1/2, this is a product here where we can raise both of these to the 1/2 power. We can do 16 to the 8th to the 1/2 power times y to the 12th to the 1/2 power like this. That's a possibility. Now, like we did before, and that's an 8, by the way, the 8 can multiply with 1/2, and you would get 4. That's 16 to the 4th. And then 12 times 1/2 is 6, so that'd be y to the 6th power. That's good. And then we can take the square roots of both of these parts. Now, square root, remember, is the second root there. So we're taking the second root of 16 to the 4th and the second root of y to the 6th like this, which means we're going to be dividing both of these by 2, right? Don't try to take the square root of 16 within here. Remember, really treat it just like an x, right? We don't change the variable when we take the square root of x to the 4th. We keep it as an x, same with the 16. So the square root of 16 to the 4th, you divide 4 by 2 and you get 16 squared. Good, that's a good number. And then 6 divided by 2 is 3 and you get y cubed. And 16 squared is 256. So you get 256 y cubed. That's one way of going out about the problem, and that will be a correct answer that I'll write there. Here's an alternative to that. Probably, I'm not going to say the road less traveled, the road not taken, but you really got to think outside the box for it. We do know that a square root is a second root, and a second root would then mean that you're raising something to the 1/2 power. When you take the square root of something, you're raising it to the 1/2 power. So what if we took this inside thing, 16 to the 8th, y to the 12th, I'll raise to the 1/2. And what if we, instead of writing it as a square root, what if we said, well, let's raise this all to the 1/2 power. Now, I know nested parentheses are kind of bothersome for people to look at, and I'd agree, but we're going to get rid of this on the next step. See, we have products with powers, raised to a power, raised to a power. Anytime you have power raised to a power, such as these 1/2s here, you can multiply those exponents. 1/2 times 1/2 is 1/4. So instead, we can write it like this. 16 to the 8th. My 8s are getting kind of bad here. y to the 12th to the 1/4 power. That's pretty cool because, now we're going to do what we did here before without a square root in the way. So now, we do 16 to the 8th to the 1/4 power, which means you do 8 times 1/4, and that's where you get 16 squared. And y to the 12th to the 1/4 power, which 12 times 4 is 3, that's where you get the y cubed right there. So you would kind of keep going to get to that part to get 256 y cubed. And that's a good alternative to this problem here. There are so many other ways. I'm not going to bother with all of them, but those are two good starting points as far as breaking up into smaller components. Do I deal with the square root immediately like it did in green, or do I wait for the square root in the end like it did in blue? That's kind of your call thing, and what you choose to do from there is, of course, also your call. And those are two different methods, and I won't promise you two different methods for every problem. All right, number 9. So you have 27x cubed all to the 4th power, and we're taking the cube root of that. Now, I don't plan on taking 27 to the 4th power first. I plan on taking the cube root of 27 first. So maybe it's in our best interest to not deal with this 4 now with both the 27 and the x cubed. Maybe we deal with the cube root first. This step isn't necessary to write, but, maybe you need this perception of saying that, let's do this first and then do that second. Break it up into smaller components. My small component is I'm going to ignore the 4th power for now. I'm going to do the cube root first. So I'll go ahead and do the cube root of 27 times the cube root of x cubed and raise that to the 4th. See, we're doing the cube roots first, making our numbers smaller. I don't care to do 3 times 4 first, 3 divided by 3 first. That's neither here nor there. That's fine. But the cube root of 27 is important, and we might as well stay consistent. So cube root of 27 is 3, as we've seen a lot of. The cube root of x cubed, 3 divided by 3 is 1, so that's just x. And we are raising 3x to the 4th power. I'd say this is a good approach for this problem. So remember, you are raising the 3 to the 4th power as well. I don't think I need to write that in between step there. But 3 to the 4th power is 81. And of course, x to the 4th is exactly that, x to the 4th. So there's an answer there. We get 81 x to the 4th. Number 10 is very similar. In fact, number 10 looks like it has smaller values. It almost doesn't seem painful for us to do 8 squared and x cubed squared. If you'd like to see an alternative to what we did last time, maybe this time you say these numbers are small enough that you feel comfortable using them, even taking the cube root of whatever 8 squared is. So, hey, what if we square them first this time? What if we go ahead and say, all right, we got to square 8 and we get 64, and we got to square x cubed. Hopefully you're fine with me skipping those steps. And 3 times 2 is 6, and therefore we're going to be taking the cube root of both of these, the cube root of 64 and the cube root of x to the 6th. Now, the cube root of 64 is 64 is a perfect cube. That is 4. So the cube root of 64 is 4. And the cube root of x to the 6th, we will divide 6 by 3 to get 2, and that becomes 4x squared. As you can tell, I'm skipping more steps. This is something that, you can lend yourself to once you start to get the gist of your properties. Not every property needs to be written. I do think it's worth your while. When they say multiple steps, I do think it's worth your while that you are getting that in-betweener before you get to your final answer. Not all problems would be 2 steps like this if you skip them anyway, but deal with one part and then the other, and you're good. And there's an answer there. All right, so number 11. It's a lot kind of like numbers 9 and 10, only now there are 2 things combined. So, I will show you 2 different ways to do this because I know something very special about this problem. I'll show you the more kind of special way next. But the first one is treat it like you treated the past ones. Now, I don't think I want to do 8 to the 4th power, so I will treat number 11's simplifying of this a lot more like I did number 10. Let's do the roots first. Let's raise to the 4th power after, and same with this one as well. I do need to mention something about this part, though, that you're going to be a little confused about. So let's see. Let's start with the first one. Because I can take the cube root of 8. I can't take the 6th root of 8 and, be all hunky-dory. So the cube root, remember, we're going to do cube roots first. Let's do the cube root of 8, and that's 2. The cube root of y cubed, 3 divided by 3 is 1, and that's y, and we're raising it to the 4th power. You see, even though the 4 was inside the cube root, that doesn't mean I have to evaluate that first. And that doesn't mean I have to write it like I did with the previous problems. If you know something you can do there, that's perfect. So that's a good simplification of that. And that actually becomes, just to write this part, that 2 to the 4th is 16. And then you get y to the 4th there. So that's this guy. Now this guy's a little tougher. And this is why This is where looking at this in different forms is very helpful for us. I don't know the sixth root of 8. It's not a perfect sixth power thing. But as this is raised to the fourth power, we go to this idea, this property that if you take if you take a root of a power thing right here inside the radicand, that you can rewrite it as a fraction. And maybe it's worth us talking about this as a fraction, because we have a 4 divided by 6 going on here. Maybe we look at this part instead as 8y cubed to the 4/6 power. And the only reason I mentioned that we write it like this is so you can actually see that fraction take hold. Instead of saying let's divide it, as a fraction you can say let's reduce it. 4/6 is 2/3. Why does that matter? Because now if this was a 2 and this is a 3, hey, it's a cube root, right? I can take the cube root of 8. So, maybe that you can reduce it here like then and there. And that's great if you can reduce it then and there. But if you need that fraction equivalent just for that moment to see what you're going to be doing, let's go ahead and take the cube root of 8 and the cube root of y cubed. And, you'll get 2y again, actually, by the way. So that becomes 2y. And then this is squared. And now we get to square 2 and square y. So we get 16y to the 4th times 4y squared. All right, well, what does that become? Well, that 16 times 4 is 64, and y to the 4th times y squared is y to the 6th. So you get 64 y to the 6th power. That's a very level 2 problem. You know what I mean? I think number 8 was as well, but this was a very level 2 problem. Had some stuff there. Now, that's one way to do the problem, and that's, all told, that's kind of how you'd have to do the majority of problems that look like that. But this problem has something else that's special inside it. And by the way, keep in mind that 4 and 6 thing is 2/3. I'm going to use that again. Here's an alternative. Something special about this problem is that, when you call something a base, how this thing's all raised to 1 power and all raised to 1 power here. That means these are bases. When you look at these bases, what do you notice? 8y cubed and 8y cubed. They're identical. And we are multiplying something here. Now, there are radicals and all these things. We can convert them. But the idea is if we follow this property, that you multiply two identical bases with exponents in them, that you add the exponents. We can do that with this problem. Our first thing we got to do is convert this into exponential form, just like we did here. So what I'm going to do is rewrite these instead. I'll have 8y cubed to the 4/3 power, 4 divided by 3. And let's multiply that by 8y cubed to the 4/6 power. Now remember, that's 2/3. And I'm going to use 2/3 because what we're going to do here is same base. We will keep the base and add the exponent. So I'm going to use the property where we say we take this base and we add 4/3 with 2/3. And I don't imagine this is the last time I'm going to be doing something of this ilk. As long as we have same bases, they don't have to be complex bases like 8y cubed, it could just be an x. But as long as we have something like that, then we can make this happen anytime we want, need, or it needs to satisfy what we have to do with our final answer. And this is one of those cases. Now, 4/3 plus 2/3 is 6/3. 6 divided by 3 is 2, and that's a beautiful integer that we have there. So this cleans up into this, and no other problem would have it. If these were not identical, we couldn't do that. I'm sure there are some ways that you can manipulate them. I've definitely run into problems of that ilk. When we deal with solving exponential and logarithmic equations, that's actually something that we do play with, we tinker with. But right here, we already have same bases. We multiply the bases and we add keep the base, add the exponents. So anyway, we square we square 8 and we get 64. We square y cubed and we get y to the 6th power. And that's the special version of that problem right there because of this unique vision that we have. And that still tailors into the idea of we convert it to a rational exponent and we reduce that fraction, which looked like something we probably had to do unless you were planning on doing 8 to the 4th and you knew the 6th root of whatever that number was going to be. All right, so very, very level 2 kind of problem there. Let's take a look at number 12, which also can have some level 2 bases to them. What I'm really looking at when it comes to simplifying, of course, is we can evaluate our numbers. I can take the square root of 16. I can take the cube root of 8. And so I am looking to kind of, get a split on this, if you will. Square root of 16 times the square root of x takes hold on the top. The cube root of 8 times the cube root of x takes hold on the bottom. And the square root of 16 is 4. And the cube root of 8 is 2. And, one might argue that 4 divided by 2 is 2. So one might argue that right here you'd be, done. After all, I've even mentioned, if you can't take the square root of a variable, depending on the exponent it's raised to, then you would leave it inside that radical. But it's a little different because we have two different radicals and they both feature the same variable, which means perhaps there's a way, especially with division or multiplication, that they can perhaps interact. Never forget the fact that radicals are rational exponents. The square root of x means x to the 1/2 power. The cube root of x means x to the 1/3 power. Dividing, here's exactly what I was saying, dividing variables of identical bases, or dividing identical bases, means you subtract your exponents. Keep the base, subtract your exponents. So this can be written as 2 times x to the 1/2 minus 1/3 power. Not everybody's favorite, subtracting these exponents. We have we need to get a common denominator here, but whatever. Times 3 over 3 here, times 2 over 2. Here we'll get 2 times x to the 3 over 6 minus 2 over 6 power, which is 2x to the 1 over 6 power. Now this could be an answer. This is fine. I'm asking my students to write it in its radical form, so we'll bring this back. X to the 1/6 is the 6th root of x to the 1st, so the 6th root of x. So I'm going to write this as 2 times the 6th root of x, like that. And if you're asking why, it's because that's likely what you'll see me do with numbers. If I have to simplify a radical and it's still left with a number inside there, I want to write it in the same radical as my variables. I have hiccups. I'm going to pause this in a second. But I'm going to keep in the same radical there. You could do that with rational exponents. Just you don't see it as often with numbers. So I'm bringing it back. Give me one moment. All right. Hopefully I'm hiccup free as we move on. So 2 times the 6th root of x. 2 times the 6th root of x. And I tend to get in this here. I'm going to try and do it without the times symbol. What I don't want you to think is, I don't want you to think I'm writing 2 to the 6th. So I'm going to try and do this. 2, and I'm going to get a nice large radical. There, does that look okay? 2 times the 6th root of x. There, I think I made the radical too big on that side. But there we go. Okay, so there's that problem and there's that answer. Very level 2-esque. Now number 13, I could definitely see number 13 falling under level 1. Not saying it's as easy, but I think it's very achievable. That one on top is, hey, that's great. Now this is to the 1/3 power, which means it's also the cube root, right? So what are we going to do? We're going to take the cube root of the top and the cube root of the bottom. And, anytime that we feature numbers, it's best to probably evaluate them in that form with the radical instead of the rational exponent. And I think you're comfortable enough seeing this as 3 divided by 3, kind of thing like that. So the cube root of 1 is 1, as 1 times 1 times 1 is 1. And the cube root of 27, as we've seen before, is 3. And 3 divided by 3 in this case for y cubed is 1. So it's 1 over 3y. And look, that's it. I don't see that as a level 2 problem compared to that of the other things, because there wasn't much to explore on that. Just because it was a fraction, doesn't really mean too much on that. So that was number 13. And 14, I'm not saying it's a level 1 problem, but 14 and even 15 right here, they are a little more rudimentary compared to that of 11 and 12. I'd say those were a little deeper. So with this, it's really just let's take care of this part, let's take care of this part, and then let's combine the ranks anywhere we can. So x squared times y all cubed means, I'll write this one out a little. We're going to cube x squared. We are going to cube y as well. And then times y to the 4th. The square root of y to the 4th there, that being a 2, means we're going to be multiplying that by y to the 4/2 power, So as I clean this up, 2 times 3 is 6. Y cubed is y cubed, and then y to the 4/2 is y squared. Now, I won't leave it like that, of course. I will be multiplying the two y's together, which means I will be adding the 3 and the 2, which will get us y to the 5th power like that. So x to the 6th times y to the 5th. A lot of steps in between that weren't really needed. Well, this step really wasn't probably needed there. You probably won't see me do something of that variety down the line there. All right, number 15. Although these are rational exponents there, as long as there aren't any numbers and as long as they need to interact with other values such as this one here, I think it's worth its while to keep it as, rational exponent. Don't convert it to a radical unless it's the very end of the problem. And we need to. So x to the 1/8 times y to the 4th to the 1/4 times z to the 1/2 all raised to the 8th power means you are going to be doing 8 with all those. So that is x to the 1/8 times 8, or sorry, excuse me, to the 8th. And then y to the 1/4 to the 8th. And then z to the 1/2 to the 8th. 1/8 times 8 is 8 divided by 8. That's 1. So you just get x to the first power, or x. Here you have 8 divided by 4, which is 2. So that's y squared. And 8 divided by 2 is 4. So you get z to the 4th. And that actually is your answer. You can see how these ones do seem to clean themselves up a little. Not clean themselves up a little better, but be a little more efficient in just solving it. I couldn't even really tell you other strategies that I'd prefer. Right? Sometimes I say there's more than one way to do a problem. I'm not looking at other ways to do that problem. All right, number 16. This should probably say a 1/5 right there. So let's just deal with that bottom first. X to the 10th to the 1/5 power. 10 times 1/5 is 10 divided by 5. So that's going to be 2. So on the bottom, I'll get x squared. Okay. Now the top. We have an instance where you would be looking at doing 8 divided by 3, right? X to the 8/3. But the difference is, that's not an integer value. So we're not going to write the answer as a decimal. We're also not really going to write it as a fraction either. The goal is, just like when we simplify any other sort of radical with numbers, is we do have to find still perfect cubes to pull out of here, right? I could do x to the 6th, the cube root of x to the 6th, and x to the 6th is smaller than x to the 8th. I could do the cube root of x cubed, which is smaller than x to the 8th. There are perfect cubes that exist inside there. Anything that's a multiple of 3, x cubed, x to the 6th. And, if we split it up, this isn't the way that I always write it. I'll show you kind of the form that I would do down the line if I need to. But if you split up x to the 8th into x to the 6th and x squared, and of course they have to be in the same cube root radicals like that. This is good. I chose 6 because it's the largest multiple of 3 that's less than 8. So I can take the cube root of x to the 6. You do 6 divided by 3, and you get x squared. Now I can't take the cube root of x squared, and there are no other radicals it can interact with, so it's going to remain as the cube root of x squared like that. So I have x squared times the cube root of x squared, all divided by x squared. A lot of x squareds here. Now these x squareds are rational numbers. They're not inside of a radical, so they can interact with each other, such that I will divide x squared by x squared, and then you will get 1. And then you just have the cube root of x squared left, and that would actually just be your final answer. So you get the cube root of x squared. That's one way to do the problem. Now, one other way to perceive that portion of the problem, there we go. One other way to perceive this portion of the problem, what I did right here, instead of writing this part and jumping right over here, what I do with my students is, I treat it as 8 divided by 3, right? Think of it as long division. 8 divided by 3 says, how many times does 3 go into 8? Well, that's twice. 3 times 2 is 6, and 8 minus 6 is 2, and 2 is your remainder, right? 2 with the remainder of 2. This 2 right here would represent the 2 of that guy. And then this 2 as the remainder would represent this 2 right here. And then the 3 is kind of the divisor still. So 2 wholes can pull out of there, right? 2 perfect cubes come out completely of a radical, and 2 remain, inside there, right? So that's kind of the idea that you would do there. You don't have to write that out. You just kind of say that out loud. How many times does 3 go into 8? 2 times. How many remain? 2. Okay. One of my students did this problem a different way that I kind of enjoyed looking at, and it is a lot like it's a lot like number 12. In that even though these weren't written as radicals, well, this one is, treat them both as rationals. This is x squared. This is x squared on bottom, but on top, this is x to the 8/3. I actually thought this is probably the way we probably should do this problem. And just divide by subtracting. It becomes x to the 8/3 minus 2. Or minus 2 over 1, because we're going to get a common denominator. So right here, we can go ahead and multiply this by 3 over 3. And that becomes x to the 8/3 minus 6/3, which is x to the 2/3. And x to the 2/3 becomes the cube root of x squared. That's a really good way to do the problem. But as we deal with some other radicals potentially in this way, I want to make sure that you still know how that works, because this might be the only thing that's in the fold. Maybe it's not going to interact with another number at all, and you still need to know how to pull something out. But that's a really good way of doing that problem. I liked it. All right, those are the level 2 problems there. Now we're 45 minutes in. We have level 3 problems to still take care of. We have 6 more. 6 more to do. Now level 3. Oh, if you can do these. There is nothing on the quiz or test involving, true or not, I don't know. Some of these other problems are actually less intimidating than others. Take number 17, for example. I don't have too much problem with 17. It could be a level 2-ish. 17's big thing here. You know, you do have a negative 1/2 right there. Okay, there's that separation. Make sure we know that. Now, I've mentioned before that with a negative exponent, I want to immediately turn it positive. And I do when I work with the exponent. But until then, I have a set of parentheses and something here that I can simplify. 1 over 25x times x to the 9th power. First of all, there's no reason that this couldn't just be written as x to the 9th over 25x. Right there. And that kind of helps you, because seeing it as division means that, well, we can do something with those x's. If you can simplify something inside of a quantity, and I'm not just talking about these kinds of problems. I mean, if it's a regular polynomial thing where you're distributing or something, if you can combine like terms on the inside of something, do that first before you deal with things outside of it. Now, we've had, before I keep going on the problem, we've had other problems where this was a possibility to consider, like number 4. Right here, where there was a negative exponent and I did a whole fraction flip and stuff, but 8 over 27 can't simplify. I can't reduce that fraction. If I could, if this was 9 over 27, I would have turned this into 1/3 before I did any flip. So I recommend simplifying the inside. You don't have to. You have to eventually. But if you do it earlier, then you don't have to do multiple things engaging with this, negative 1/2. So let's just deal with it now. X to the 9th over x means I can divide out an x on top and bottom. I remove the x on bottom. I remove one of the x's from the top, and I'm left with 8 of them. And that's my simplification. So now we have x to the 8th over 25, all raised to the negative 1/2 power. This is where I like to turn the exponent positive, and in doing so, that means I also flip this thing right here. And that is now raised to the positive 1/2 power. Now, raised to the 1/2 power means taking a square root, so we'll be taking the square root of 25 and the square root of x to the 8th. The square root of 25 is 5, and the square root of x to the 8th, do I have to write the 2 here? You could use that 1/2. 8 times 1/2 is 4. It's x to the 4th right there. So we get 5 over x to the 4th, and that is our final answer there. Pretty cool, yeah? All right, that's number 17, and that's really the way I would look about doing the problem. The only alternative, of course, like I said, is if you raise to the 1/2 power for this, and you see it as a 1/2 instead of a square root. But I did have to take the square root of 25. All right, number 18. Oh, I thought this was I'm like, no. Number 18, nested brackets and parentheses. We have 2x to the x power times 2x to the 2x power times to the 1 over x power. Okay, there's so many ways to do the problem, guys. I'm just going to do it one way. It's okay. So what I'm going to do is, as I mentioned before, if you can simplify an inside, go ahead and do it. And we do have same base. I have 2x and 2x, which means I can add my exponents here, right? So inside of the bigger bracket thing, I do have 2x times 2x to the x times 2x to the 2x means this is 2x to the x plus 2x power, right? Those two are going to add together, and x plus 2x is 3x. So 2x to the 3x power. There's something I can do with the 3 now. I'm going to leave it. I am going to now play with these two together in that, the power to a power thing means you get to multiply these things. So what happens when you do 2x, put equal signs, 2x to the 3x times 1 over x power? Well, those x's are dividing, right? X divided by x, and that, they cancel. That's gone. You're really just, 3 times 1 is 3. So you're really just left with 2x cubed. And I'd say this is probably the cleanest way to do the problem once we got to really take care of that inside. 2x cubed would be, 2x quantity cubed would be 8x cubed, like that. So 8x cubed. Yeah, a lot of other things to do there. You know, you might sit there and ask, how do we do 2x to the x power? How do we evaluate that? Well, you don't, right? X is a variable, just like this x is as well. You wouldn't do anything with that. You got to try and get it to interact with other things. In this case, it actually went away, which was nice. Now, I'll tell you this. If your final answer was 2 to the 2x power, you know, you're like, oh, I'm going to write that as my final answer. I would actually, there's something to simplify there still. The x has to stay as an x, but, you know, 2x means 2 times x, right? So what's to say that you can't take the property and, you know, where exponents multiply, it comes as the result of a power to a power? What's to say that you can't write it like this? And you know what 2 squared is? Well, it's 4. So it becomes 4 to the x power. So 2 to the 2x power is better written like that. That has nothing to do with the problem. But I'm saying that if an x still existed there with another exponent, there's actually more that you can do there. It does work like that. All right, let's move forward to number 19. We have the square root of 2x squared times the square root of 2y. I don't probably want to keep these as square roots for several reasons. Among them, I can't take the square root of 2 anyway. So, I might go back into radicals. Like this answer will probably have radicals with it. But I also have a square root inside of a square root, and you're not going to have that within your answer. I think it's best to have the square roots interact in such a way that you are raising them to exponents. This is a level 3 problem. I mean, this one here, because you are going to be nesting radicals. So be very careful here. Nesting rational exponents. So here, this first radical here, I'm going to put big parentheses around it and say this is all raised to the 1/2 power, okay? So this thing is for that. So inside of this 1/2 power, we have a 2x quantity squared. Now inside here, you also have this 2y inside of the square root, which means this is 2y to the 1/2 power, like that, okay? Okay, these are not the same base. The 2 is the same base, but because it's caught with the squared and the x, you can't really interact these the way that you probably would want them to. So these are not the same base. So there's nothing really to simplify for us yet. So if there's nothing to simplify, that means let's take care of this part here next. Let's take this 1/2 to these two portions of the product. That means it'll be 2x quantity squared. I could have cleaned up the 2x squared, undoubtedly, but I couldn't have cleaned this one up, so I'm just doing both of them the same way. So 2x squared to the 1/2 times 2y to the 1/2 to the 1/2. You following me? Both of those are being raised to the 1/2 power there. Probably should have used square brackets. Now, why do I do that? So I can multiply these two things, right? 2 times 1/2, and guess what? That's just 1. That means this whole business, that just turns into 2x. That's good. Now, this 1/2 times 1/2 is 1/4. So this is 2y to the 1/4 power. Nothing seems to have changed with regard to me not being able to take anything out here. I still can't take anything out here. I can't take the 4th root of 2 and all that. What I will do is I'll go ahead and turn this into its radical version, the 4th root of. So the 2x is on the outside right here, and inside this radical, the 4th root is 2y, and that'll be your final answer there. I'm not saying this was a long problem, but I'm saying this is a level 3 problem right here. And this, look, more than one way to do it, but square root of square root and stuff like that, and where do things belong, what do you do with them? I think really getting the rational exponent is helpful. There is a way you could have done something with these 2's here together. I'm not going to deal with that because that 1/2 cleaned things up anyway. This really probably is the best way to go about this problem here. Number 19. All right. And I'm trusting my answers are correct. I'm not looking at a key alongside this. What I'm doing is the key. It seems sound what's going on there, and I hope it's working. All right, number 20. It looks cumbersome, but I promise you there's not much to it that's really very bothersome. You could do the 4th power and 1/2 power here like that, but as long as you have a power to a power going on in this format, why not deal with these first and then kind of do everything after that? So, 4 times 1/2 is 2, so I get x squared y squared. And then 1/2 times 4 is 2, so you get x squared y squared. And, At some point, you don't let process do everything and you let logic take over. I have something divided by itself. Confirm that it is, and I believe it is, something divided by itself. Instead of saying, oh, let's square this and do that. See, we saved ourselves some time there. I didn't intend for that, but we did. And something divided by itself is 1. I don't know if that's a level, because the way that we did it, it's kind of a level 2 problem in a way, like even level 1 if you, but it's all about strategy. Level 1's about process of your properties. Level 2's about strategy, and obviously level 3 is about hiccups. But this one here, actually, most complex, I'm going to take that back, of the more complex looking problems there, because nested parentheses and a fraction, it was really fast if you kind of go about it in a way that's going to be tangible and helpful. All right, 21. 21 sure looks a lot like 19 in that, I've nested radicals there. Probably best to convert them to their rational form. So I'm going to do what I did before in that, let me erase this top part here. In that I will raise them to the 1/2 power instead. And then you can wrap parentheses around parentheses and we'll have powers to power. We'll have powers to powers there where certain things happen. You have to track what you write, though. My hiccups are back, though. I might have to... Let me pause this again just to get rid of my hiccups. 1 sec. And we're back. All right. So, let's work from the outside in. On the outside is 8th power. 8th power. On the inside, let's work with that z. The square root of z. Obviously, there are other things, too, right? But to the square root is to the 1/2 power, right? So, to the 1/2 power, I have z times the square root of y. That's to its own 1/2 power. This is so level 3. Y to the 1/2 power times x to the 1/2 power. I don't even need it around parentheses, really. But just want to kind of show you where things go there. I could color code it, but you won't be able to. And you know what would kind of be helpful is do square bracket, alternate square bracket with parenthesis with square bracket like that. You can probably follow it a little bit better that way. I certainly can. What you have to be careful of, though, is, you have these 1/2s, and you sure can multiply them, but you're not just going to do, hey, what's 1/2 times 1/2 times 1? No, because you have to remember that these carry into other parts of products. For example, this 1/2 is just to the x, right? But this 1/2 is to this product right here. This is y times x to the 1/2. You know what? It might be better to not have parentheses there. Let me rewrite that. This is y, I'm going to write times. This is y times x to the 1/2. So, this 1/2 right here is for this entire quantity right there. So you're going to raise both y to the 1/2 power and x to the 1/2. Excuse me. You're going to raise this y to the 1/2 power and x to the 1/2 to the 1/2 power. Both of those will get that treatment. Let's write that step before we kind of progress forward. So on the outside to the 8th power, we have a z. Do I need this setup? Yeah, I do. We have the z to the 1/2, and then, inside of here is just that next step is y is to the 1. I don't think this needs parentheses anymore, but y is to the 1/2 power, and x is 1/2 times 1/2 is 1/4. So x is to the 1/4 power, like that. Yeah, this doesn't need parentheses anymore because now it's on the same level as the z that's raised to that 1/2 power. So this is z times y to the 1/2 times x to the 1/4, and all of that's being raised to this 1/2 power. So now z gets to the 1/2, y to the 1/2 gets to the 1/2, x to the 4th gets to the 1/2, and all that's raised to the 8th power. So this equals, now this is all just around this set of parentheses now. So z gets to the 1/2, y to the 1/2 gets to the 1/2, that's 1/2 times 1/2 is 1/4. So y to the 1/4, and x, 1/4 times 1/2 is 1/8, like that. We kind of saw a problem like this. This was, I think, on level 2 at this stage. But now we're going to go ahead and do the 8 to these 3 as well. And 8 divides by 2 and by 4 and by 8 right here. When it multiplies by those fractions, it's going to divide. So we end up getting 8 divided by 2 is 4, so we get z to the 4th. Y divided by 4 is 2, so you get y squared, and 8 divided by 8 is 1, so you get x right there. This is an answer. As you know, I'm probably going to write this alphabetically, so I'll get x, y squared, z to the 4th as the final answer. Was that the same answer as the previous one? Let me check. Yep. Obviously represented differently. I think it's a little farther back in how this problem was represented, but that's x, y squared, z to the fourth. Very level 3. Very level 3. And, you know, it's not that you can't do any part at a time. If I just gave you this independently, you'd kind of know what to do, you know? But altogether, it's really, how do you follow your steps? We worked from the outside in to generate this, and we worked from the inside out to calculate it. You know, and that's really confuzzling. Not to mention the fact that, like I said, you can't just multiply these three together because there are other portions of this that are taking effect. It's not just these 1/2s multiplying. It's the y and the z that are also taking hold with it. Like that. All right, number 22. You got a -1 there. You know, there's just a lot involved. You know, I'm already seeing something right here where I've made mention before. It's probably, as all these are x's, it's probably worth converting these to their rational exponential form. You know, you have this 4/6 again. We're going to be able to reduce that fraction. So, in fact, you know, take a look at this. These two things I can eliminate very fast here. Let's, just ignoring this part right now, let's just look at this part here. That's x to the 2/3 over x to the 4/6, which is x to the 2/3, right? We saw that on a previous problem. So that's x to the 2/3 over x to the 2/3. Well, that part is going to divide itself onto itself. So that's just 1. Those are gone. So immediately I can cancel out that part of the problem where that's no longer a part of it. So I'm just going to go ahead and say, okay, well, this part's gone. So the only part we're looking at is just this. All right, which is, I mean, still something. Excuse me. Now, I do have a -1 exponent, and I've mentioned so many times that I'd rather, you know, deal with positive exponents. But, you know, what am I going to do? Call this 1 over? Oh, you know, you could. There's nothing wrong with that. If this is all that's there and there's no other fraction, let me rewrite this. I got x to the -8th to the 1/4 to the -1st power there. You know, that's, yeah, that's 1 over that whole thing. But, you know, it's just a -1, and it's going to interact with other exponents. Why don't we multiply these? In fact, all of these multiply together. This is not just a power to a power. It's a power to a power to a power. All these multiply. This is x to the -8 times 1/4 times -1. I'm talking about negative exponents turn positive immediately. You know, these are interacting with other exponents immediately to the point. It's not like I'm distributing the -1 into a bunch of other factors. It's just this one. Now, -8 times 1/4 is -2. -2 times -1 is +2. This becomes x squared. That's it. That other part is gone, and this just becomes x squared. And that is level 3. And, you know, this is not to say that these are the only kinds of problems that occur for level 3 as far as challenge goes, but this thing does state fact. If you could do these, there's nothing on a quiz or test involving exponents radicals you cannot handle, because these do, I mean, I'd say 17 and 20 were pretty straightforward, but, you know, these force you to strategize. These force you to perceive and look at, you know, things nested and really pay attention, you know, pick apart one part from another and, you know, see what's going on. So I'd say with that involved that if you do know how to do those, that you are well on your way of really making sense of kind of anything they throw at you. So I hope that those really felt good for you. All right, guys, that was more than an hour. That ought to do it from here. This is Mr. Robinson. Thank you so much for watching. And whenever the next one is, I will see you in it. Take care.